So now it's on YouTube.
All righty. Now, which screen did I have before?
Hey, how you doing?
How are you?
Good. How you doing?
And I did.
Those, last night with the Chinese camera,
Yeah.
these guys stacker whines about not having stars stacked. They'll stack on the points, they'll stack on this, on pixel. Or it'll, I can tell them not to stack, not to along.
Yeah.
And then it'll stack. And you got a little bit of trail.
But if you look at the pictures, does it look like there's a bunch of stars? There's that.
Well, there's about a dozen.
It's sounding to me, I'll see what that big insight does. See if it can be back to it.
We'll get started in a minute, as soon as I can remember how I shared this before.
Computers.
Chris, you got a hard drive in the planetarium.
That is not mine. Somebody's.
The computer in the planetarium is a WASI computer.
We got the external one.
That's. Yeah, I wouldn't plug it in.
We're gonna get started in just a minute, as soon as I can remember which share
Maybe that's.
I needed to do to make this work. Daggone it.
Thanks to the Muslims, and they can still play that worked out well. It's not too hard to run it. No. But speaking of ASI,
I found it was recalibrated.
Man.
It's good. You recalibrate on one gate and then the ones that are around handle.
well, so the thing is that it's handy because.
Which one is it? It is.
Recalibrated over here, it's all the stuff over here.
How big is it over here? Like 100
Well, so
Lights go.
you're on one side of the meridian and you calibrate all your pointing.
Who's ready for the
We're gonna be getting started here in just a second, as soon as I can remember how to do this. And if you are, oh, Chris, I think you have your microphone on.
You're on one side.
We're gonna be getting started here in just a second. It's got the YouTube on how to do this. And if you are. Oh, Chris, I think you have your microphone on.
Script.
We're gonna be getting started here in just a second. It's got the YouTube on it. How to do this. And if you are.
Like MBS says, start looking at them. YouTube is one that's behind.
Right, and I just muted this YouTube, but now I've lost how I had the share going.
Yeah, I mean, this is great too.
All right, just shoot me, everybody, just shoot me, because. Hi, Tim, and hi, Charlie, bear with me for just a minute.
No worries, thank you.
Really?
So that's one, we're going to share one,
You know, as far as no format to be.
going to share that one. Okay, let's share that one.
Well, it should be on.
Oh, yeah. Hey,
It's the Chinese.
I guess not.
90 seconds.
Okay, so it's under in slideshow. Nope, that's not working. So.
How you doing?
The Dave sounds like.
Just shoot me.
Playing designated photos and stuff on it.
We got a speaker. Another one.
Oh, damn it.
I'll look at the paper. Yeah. I don't know if we are evolution or something.
I've got like 3 of them open.
Are they on the theory? Let's see how you, yeah. Yeah, that's right.
Share, I don't want that.
I'm glad you tried to find that. Clear whether it's showing me. Well, the morning, cloudy this morning.
All right, that is still not sharing.
Right now, I think. It's either this morning or tomorrow morning. They're gonna be at their close.
That is still, jeez, this just worked.
Should be.
Yeah.
We were both in that state.
Yeah.
Yeah, that was south. It was literally for Jerry. Or really,
Yeah.
because the Jerry's running, you can actually see it through.
I like that. Early our phone did once and the wind was just now.
That is not.
Slow as we right.
Oh, yeah, it was, it was huge. The wind was running. I couldn't see.
Hey, Al, I could use a hand.
Yeah.
This is tanking on me. All right, I am not figuring this out.
It's like pretty low. Yeah, I did see.
I just had it too.
Plays is far away and then even on.
And then go to slideshow. And nothing happens.
That's Orion.
Then
Yeah, yeah.
spot presenter doesn't bring it up there.
That's the Aurora. Whole
I
Saturday.
didn't see it, I was late when I saw everybody's pictures.
Slideshow.
Yeah.
And
She, Lori.
can't,
Where you go?
I can't get it to go up there.
From Hampstead that they.
Duplicates settings,
That they saw it.
but then I can't run the slideshow.
Right, yeah. That's what PC are.
I don't even know what to say at this point.
There's some setting, but there's supposed to ask the, but we have some.
No, I just had it,
Before we got there, they were out.
just had it. And it was working,
It's over to another friend.
and now it's not.
They said, no, stay, and I was like, oh, no. It's all asking for fishing and who gets to use the boat. And
All right, we'll just get started and see what happens here.
we're very.
So we're gonna start with a little video.
Well, I had one.
See if we can do this.
High school, and we were the soul train. And we both lived at the beach of one year.
The vast band of our Milky Way galaxy stretches across the night sky.
So I have a lot of friends that, you know, all your best friends are from college.
It's a contrasting combination of bright starlight and dark dust lanes. Stars along the pancake-like disk are seen in short wavelength infrared light, while long wavelength infrared light features the dense dust clouds. These dark dust clouds are places where new stars can form. Newborn hot stars heat the dust clouds, and their cores glow brightly. The Eagle Nebula is the birthplace of a cluster of luminous young stars. infrared light can trace the dusty skeleton of the nebula. And X-ray observations reveal over 1,000 stars in the central cluster. The largest stars in the cluster emit strong stellar winds and energetic radiation, which stream across the nebula and shape the iconic pillars of creation. Made famous by the Hubble Space Telescope using visible light, the pillars are equally amazing in the infrared view of the Webb Space Telescope. Examining their structure in 3 dimensions, they separate into individual clouds. The right pillar is closest and is backlit by the star's intense radiation. Glowing ionized gas streams away from the pillars. The infrared view of the central pillar reveals vibrant evidence of an embedded protostar. The top of the left pillar is directly bombarded by energetic starlight. Dense pockets of dust resist the erosion and create narrow, finger-like peaks. Lower down, jets from a newborn star shoot away from the peak. The semi-transparent body of the pillar lies in the shadow of the dense top. A newborn star blazes at the end of this peak, underscoring the nickname, Pillars of Creation. Stars form in these dusty pillars. The dusty pillars are shaped by emissions from young stars. The young stars form within giant dust clouds. Dust clouds and stars are strewn across the plane of our galaxy. The interplay of stars and dust creates cosmic structures on many scales.
Okay, we're going a little high tech this time, and hopefully we can keep going high tech, which means that just so you all know, we're also streaming on YouTube. We probably don't have any audience there because nobody knows we're doing it yet, except for you guys. So we'll see how that goes. So this is the what's up portion of the meeting, which normally starts at 7 and goes to 7:30. So you just saw the NASA short video, got some observing information from the Astronomical League, and then some sky watching. So from the Astronomical League, we have the Navigating the August Night Sky, which gets sent out to all members. And of particular importance, I wanted to point out this area that's almost overhead right now. It's between Arcturus, that bright orange reddish star, and Vega, that real whitish one that's almost overhead. And this little tiny constellation, actually, that's Keystone. Use the right part of my bifocals here. The northern crown here is Corona Borealis, and there's a particular star in there that's going to be going nova. Now, one of the common questions that has come up is, well, what's the difference between nova and supernova? Because people will say it's going to go supernova. Well, it's not. So I put a dictionary definition here that Nova is a star that suddenly increases in luminosity and then gradually returns to its original brightness over periods of weeks to years. It could be a little less too. What's happening is you've got this red giant next to this white dwarf, and over 80 some years, it's sucking its mass off, and all of a sudden, what do when you overeat at Thanksgiving? You belch. Well, that's what this is going to do, and this belch is in the form of a nova. So supernova is totally different. It's when a star suddenly increases in brightness to many millions of times its original intensity. And that's a completely different kind of thing that happens. So in Corona Borealis, this little C shape, which is a crown, the easy stars to find are, first of all, that orange Arcturus and that white Vega. And then it's in between. And the way you find in between is you kind of creep along about a third of the way between these two stars. And you can first of all see this Gemma, somebody can correct my pronunciation, but it's basically the main jewel in that crown. Once you find that jewel, because that's going to be a star you're going to be able to see more easily, at least under bare branch skies, you'll be able to then discern somewhat of a C or a crown shape. And once you do that, know that this TCRB, or the T star in Corona Borealis, is off to this side. You and a whole mess of amateur astronomers should be looking every clear night, because, come on, Marilyn, don't cloud up on me, because you will be able to see this thing when it does go nova. It will be spectacular. If you would like to also take it a step further in your observation, and you don't need to be a member of WASI or the Astronomical League, but all WASI members are members of the league, you can put in for the T Corona Borealis Observing Challenge, Special Observing Award, and get a certificate. You need to observe it once beforehand and follow the directions for how to note that. And you need to note it, observe it and note it when it's gone nova. And you send those in and you get a lovely certificate from the league. Moving along, I do have some handouts for this August night sky over here on the free end of the table. Skymaps.com. There's also a link under the outreach resources on our website. We'll give you the free download that they put up every month. If my PowerPoint will work, and you wouldn't see so many circles. So I'm going to use my cursor here to kind of guide you through what I've got. First of all, overhead, you got the Corona Borealis. By the way, common question is when is it going to belch or burst or nova? Well, your guess is as good as mine, but since it's on a regular schedule, by the way, this is also called the Blaze Star. The best guess right now is probably September, but it could be tomorrow for all we know. But keep an eye on where this constellation is so that it'll be easy to find when things happen. Another big topic in the news, other than the elusive aurora, has been the Perseids, named for where they come from and radiate from in the sky, Perseus. This is the section of sky that you want to be looking at. So if you're here at Bear Branch Lake, you're going to be looking over to the left of the observatory as the stars rise above those trees. You'll also see about that time rising the Andromeda galaxy, or the Andromeda constellation, as it comes up with the Great Square. And very much with binoculars, not so much here, but from a dark site, you can see this with your naked eye, a nice little oblong fuzzy blob, as we like to call our objects in the sky. And that's the Andromeda galaxy, which is the only object that you can see with the naked eye that is not in the Milky Way galaxy. Straight overhead this time of year, and shown on this August map too, is the summer triangle. So very easy to find when you look for the brightest stars. The brightest one being Vega, which is in the tiny little constellation Lyra, and Deneb, which is the tail of Cygnus, the goose or the swan, depending upon your tradition, and Altair, which is in the middle of the Eagle constellation Aquila. And together, they just make up this nice little asterism, meaning it's not part of the official 88 constellations in the sky, and gives you sort of a place to ground yourself when you're looking for something specific. For example, if you happen to have a telescope and are looking for the Ring Nebula, which is M57. But I can't get past the August map without mentioning that there is this time of year, this lovely constellation Sagittarius, which doesn't mean a whole lot in its entire form. But when you look at the asterism, the teapot, then it gets really cool. The teapot is pouring its tea down to the southern part of the earth. But the neat thing about that teapot is that somebody has turned the kettle on and it is hot because that steam is rising up and creating all that good Milky Way that you see in the sky. So if you're in a light polluted sky, like a lot of places in Maryland are, and you want to know where the Milky Way is, but you're not sure because you're not seeing it with your naked eye, 2 clues. First one, the most obvious one with less atmosphere to look in or look through because you're looking up, is to find Cygnus or the Northern Cross. Cygnus always flies the length of the Milky Way. So at least you get a sense of what direction to look for that Milky Way. And then if you're fortunate and it's summer month and you find the teapot, think about that steam rising, the Milky Way steam rising. Now, very important for tonight, actually, is that the moon is going to be near Antares. Antares is that beautiful red star that's in Scorpius. This will be along the part of the sky that when you're on the grassy knoll up near the observatory, if you look between the observatory and the nature center, that's the part of the sky that you will see the teapot and Scorpius in the southern part of the sky. So we're going to have an occultation that's visible. I don't think you're going to have time to get there today. But if you did, and you had a transporter, you could make it to French Polynesia or the Cook Islands, then you would see this lovely occultation. Otherwise, you'll just have to imagine it for tonight. So do know that on the back of these sky maps, there's always some interesting information. In particular, they tell you what you can see with the naked eye, with binoculars, and also with your telescope. So in particular, you want to look at Antares because it's a red supergiant named, the name means rival of Mars. And sure enough, starting out beginner observer, if you were looking in the sky, it might be confusing with Mars. Forget that it's in the wrong part of the sky because it's not part of the ecliptic, but that's okay. It's the same shape and color, depending upon where Mars is. Then Polaris, by the way, is it's got a companion star that's not related. So if you've got some telescopic equipment that you can look through, you can look for its pal. There's another pal that's not a binary, but 2 stars together that you probably have seen in the handle of the Big Dipper. Big Dipper is this part of Ursa Major, the Big Bear, and Mizar is in the handle right there. So that's always a really cool thing to find because they say that if your eyesight's good, you can see that split with the naked eye. So skipping ahead, there's another Astronomical League challenge going on right now that they have morphed into a full-blown new solar program. Challenges, typically you only get a certificate, and programs you get a certificate and a pin. But if anybody participated in the Parker Solar Challenge, there was a great surprise in that a pin and a certificate was gleaned. Oh, dear. Okay, so on YouTube, we are on Zoom also. Oh dear, on Zoom also. Stop share. Let me try to share another way. Portion of screen, maybe. We'll do that. You got it now? All righty.
Thank you, Chris.
Yeah. So for the astrologers in the in the audience, just know that Mercury retrograde has a special meaning to you. It impacts some communications and electronics. For astronomers, it just means that it's going a different direction in the sky. I kind of scratch my head at times like this, but okay. The Astronomical League on the Solar Maximum Observing Challenge requires building this little homemade magnetometer. Now, I'm not the most technically advanced amateur astronomer by any means, but this one I was actually able to do. I actually paired up with Al here to do it. You take a soda bottle, and there's directions online in a link, and a thin thread, and you're gluing it, a straw to a magnet and a mirror that you have a laser that's going to point at and then point to a scale, in hopes that you can use your homemade magnetometer to try and predict aurora. Who has looked at the space weather webpage before? Who has had their mind boggled when they look at all the data that's there? Yeah, and how accurate do you think that space weather prediction is? Well, not nearly as accurate as our Channel 4 news guy or whomever. It's obviously a lot more complicated. So far, having done about a week and a half's worth of observations this way, I've noted that yes, indeed, there is a lot to learn, but that's part of the fun of doing these challenges. There's also a lot of web page cutting and pasting that happens with this particular challenge, which all the observations is up to one a day can be used to put towards the new PIN program. What you see in the lower right-hand corner here is this lovely, of course, I had to use purple crystals sands for my bottle and put a little couple decorations on it. But basically my cat toy is set up here on top of a jar that's separated from this very, very sensitive hanging magnet. And it's shining a laser point that's reflected off this mirror onto a wall. And if it all goes well, and I'm on my second setup, the scale goes off in one direction, then just like the KP meters that you see, or KP indexes you see on the different Aurora websites, will also be going off the deep end. And then you see this little tiny red bar here? Well, everybody who was looking for Aurora that night, which I think was the 11th, and they were out at 2 o'clock in the morning, had great shots with their cell phones. Some of us the next night, not so much, because the next night it all waned, and such is the nature. But fun little project. If you're interested in that, it's one of the challenges. I have to mention that for those who like a low degree of science challenge, we are having hosting an event of International Observe the Moon Night, September 14th, which is our regularly scheduled monthly star party. More on that when we get to the outreach portion of the meeting. But know that you can get a participation certificate that you can download yourself for having come to this event. And they are occurring all over I believe the world, but certainly the US. And there'll be freebies and some other cool things. So what you got to do to get the challenge certificate from the league is to do an activity, an outreach activity. But if you participate in ours, that counts. And you observe the moon anytime between September 14th and September 21st. You make a sketch or an image, and you have to be able to identify and label these 10 Maria. Piece of cake, especially since they post some maps of that online that coincide with this challenge. So let's see. I just want to point out to folks, this is kind of a messy slide, but if you remember, you have access to our Groups IO. Our Groups IO has a nice wiki that actually Chris had started up, and we're adding a little bit at a time. This little wiki is just a bunch of links, but these links go to lots of really cool resources. There's the date and time. One question I had gotten from somebody this week, and she'll be nameless, but she's in the room, is when are the meteor showers? Well, that link will bring you right to it. Our sky maps are linked there, as well as some other more into the weeds pieces of data, and even some free astronomy software. So if you are not on Groups.io and you need a link to it, let us know. One of the other links also gets us to one of the couple of different comets sites. Heavens Above is one of them. And one of the comets that's up right now that should be pretty easy to catch with your telescope is the 13P Olbers. So keep an eye on this if you're chasing comets. And know that the Astronomical League's webpage also contains a lot of really useful links that I encourage folks to take a look at when you have time. You can also get when the phases of the moon are happening. And I want to keep it so that our guest speaker is not having to start late, but I will go straight to asking if there are any questions. Yes.
So we're able to know when the aurora is going to sort of, I guess, glow in the evenings by using the bottle or magnet and laser method?
It's a magnetometer, and actually the space weather websites have magnetometers across the world that do the same thing. So in this teeny weeny little image here.
So would it react in the daytime before the evening to plan to view that aurora?
It's not a daytime, nighttime thing. It's more of the particles that are hitting the magnetosphere of the Earth, and a magnet hanging there is going to pick up on that magnetic activity.
Right.
And that's the fluctuation that you see.
And it's that sensitive.
Yeah.
We should make a permanent one and add it to our.
Well, I will tell you that I have to sneak down the stairs to the basement, because if I go down too quick, even though I've taped this bottle shut in the meantime, any kind of movement around it, vibration makes it shake, and then you gotta wait for 20-30 minutes for it to calm down. So I would say it's very sensitive. And I don't know if there's a place that doesn't have a lot of magnetic stuff going on in there that would be good to put it, but I hear you.
And that's because you're suspending the magnet itself, so you couldn't tension a string through the magnet.
You don't want to. You want it to have enough looseness that any magnetic change it's detecting. Well, it's also going to be detecting vibrations from your air movement without the wind per se, but the percussive impacts on the air as you're sneaking up on it. I even put my watch behind my back when I reach for the laser.
Video.
That's amazing.
For the video.
Real quick.
Whoever
It's square kilometer of black hole and putting us into the sun.
Okay.
I'm genuinely curious.
You'll have to ask that question again.
Let's say that you were able to take a little spoonful of black hole and pour it around the sun. What would happen to the sun?
Well, I don't think your spoon would last. Okay, anybody else? Okay, Kurt just stepped out.
I just have to feel that it just kind of popped up in my mind.
While we're waiting for Kurt to come back and introduce our speaker real
Maybe I
quick.
can cover that. I think that spoonful would be about the size of the Earth. The Earth is still pretty small compared to something probably just falling or something. Depending on what came to it on that.
While we're waiting for Kurt to come back and introduce our speaker, let me just say that on the left side of the table over here, we have 8 different door prizes. Take 2 sets of tickets, keep the one that says keep this coupon, put your second one into any of the 2 cups that you're interested in winning. The right side of the table has got freebies and also some of the new WASI pamphlets that you're welcome to. That's a good book. The whole series is, what's that? Yeah, I think we need the lights for the speaker. And Kurt, if you want to introduce your speaker. Kurt,
What now?
if you want to introduce your speaker
Okay. What
and
we're gonna
Jackie will
say,
get the
Mom?
lights.
Oh.
And of course, there are refreshments in the back.
He brought
Goodies.
gifts too.
Awesome. We love gifts.
So, oh, these are new.
Yes, they are. Courtesy of Bear Branch, I'm sure.
Yeah. You can set it up here.
So I guess we'll take a minute while he gets into Zoom and whatnot. Take the pressure off. Please sign in the back.
For a short presentation.
And for stuff.
What I particularly like about it is how he mentions the life of common people in the high importance. And then he really tells us what's important in terms of the main themes that you should have gotten. That's probably
The last book in that series, Never.
Yeah, that's about civil rights.
Yeah, we have to put this thing on.
Oh, really?
Oh, and it is a hard style.
Oh, so trilogy.
But the last one in the book series is Never.
Oh, I've done that.
Have you?
I have.
That really makes you stop and think.
About the president of uses nuclear war.
Yes, that's the last one in the series, but you can read them all. So.
And how nuclear war.
Kind of makes
You
you-
have a dog.
It's not like keyboard, so I put a piece of wood over it.
You
I
have-
take
Dog, because we have hair balls sitting around. Cat night. We have this many hair balls. that we have.
So for those who are online, just be patient for us while we're getting our act together here.
Going into the
Wi-Fi.
Just put in on a picture.
Yeah.
Well, you know.
And for those who are on the phone, just know that we're transitioning. So
Meeting and video.
hang in there.
See if that's one.
Circuit.
Okay.
And turn the laser on.
Okay, then you wanna go to.
I wanna see if I could just, okay, just give her a battery.
The Olympic at Westminster.
Lots of W.
Westminster Astro.
We're just transitioning.
Earlier.
Join the meeting. Join Zoom, yeah, try that out.
Please just take it. That's what you're there for.
Okay. Yes, well, yeah. And I think you also have to turn your speaker volume off. Like it. Okay.
Should we waste some money this year?
Lori, the tickets to this.
I'm trying to get my feet on. You start going. One good thing, that's why you can get her, everything's open. Why did I go?
You see a user DJ, is DJ joined?
Yes.
Okay, yeah, you're on.
Make sure I got it. Well, I'm the black hole and get there. It's not. Great.
Why don't you share your screen?
I'm sure. We just set up. As soon as we got out our phones, that's why they allowed it. So crazy. So that's how really think it's like nothing for nighttime. So I think it's something. That's saying. It's not for me. So you're gonna call that.
Not on my screen. That's not on my screen.
It's not my screen. I see it on here.
Well, you can see it. Yeah, we can't see it.
Oh, wait a minute, I got rid of that thing that popped up in the middle. Yeah, but that's definitely not my screen.
Oh.
Well. Why
can't I get rid of this?
Right.
It's good because your mouth shows up. I give you a laser.
I'm still there too.
So I think it's just there. That's this camera right here.
Yep, so.
And there's your microphone.
It'll pick up anywhere in the room.
Okay, it's omni.
Thank you. Testing.
Blu-ray.
The only thing I'll say is that
The first
this secret video. That's what and something I will take this video, you stretch it out. Right, exactly. And Spain should be right. Just on top of it, right, or exactly. Spain. It'll be cloudy. Like under Lucia. Oh, wow.
And whenever you guys are ready, just let me know and I'll hail the troops.
How many people are online? How many people are
Posters, are you allowed to put up posters down here?
No, we're not.
Then you can just give them away then. I thought that you might put them up here.
Yeah, we,
But you can give them away as a door.
I do,
Because I only have two posters, so.
I do-
Add it to the door frame.
I do snag them. And we have a bulletin board out there that I change, right now it's all black holes.
Why don't you come up and take a look? And take first pick for
And then
the club,
I've
and then let
got
me
actual outreach stuff, but for visual aids and stuff. that you can snag.
The extra toast. They're pretty tasty. Yeah. Well, right outside. And that's what you do, we're gonna say, and go back in.
Feeding the sun the whole time. So it's just like, it's almost like digging a hole in like a mole kind of thing. You would, because it's a gas, the sun of the gas, it would just fall right through and you wouldn't see it, and it would just disappear. And eventually it would just have to see the sun of somebody. Okay. Remember this question, let me ask you this question. If oxygen is gas and a black hole were, let's say we had a black hole that was because of like, right? You know, that big as that. And you slingshotted it, where did the, like, and you kept it circling, it wouldn't eat the atmosphere constantly? So we would, how long would it take to find a black hole? Yeah,
that would be soluble. Never care or anything. Yeah, you can't.
And so you
can't do multiple.
Unless I. So it's up to you guys when you're ready.
Okay.
Well, so my body was like stretch.
Yep, and then, but then you're small, and by the time you get it, you'd be.
Oh, it would be like this kind of thing. And my body would be like, rip stretch. And are you familiar with Simpsons? So they did an episode where it was like a black hole, and they pressed the black hole and the finger stretched, and they like pulled away, and they were like almost like little tentacles. If you had a photo this side, you gotta have the mask.
We're gonna get started.
Evan?
Attention.
I'm gonna have Gary run the meeting.
Yeah, you should.
Should have brought my gavel. All right, go ahead, Kurt.
Okay, well, I'm pleased to introduce tonight's speaker, Dave Uselmann. He's coming from the Space Telescope Institute, although he supports multiple missions, not just the Space Telescope, but also the James Webb. And like TESS is another one that you might have heard about. Anyway, he's an astrophysicist. He earned his degrees from the University of Wisconsin at Madison. And among those, he has minors in history of science, mathematics, as well as computer science. Now, at the Space Telescope Institute, his duties include advising on cloud orchestration and compute resources for various projects. As you know, there's lots of data coming down nowadays with the modern versions of imagers and things. Used to be, you know, gigabytes of data. What are we doing with all that? And then it was terabytes of data. Now it's petabytes and even more. But anyway, back to the introduction here. Among his many duties, he processes new and historical Hubble data for scientists. Remember, Hubble's the old space telescope, and the James Webb's the new one. He evaluates proposal observations for Hubble and the James Webb telescope before the selection for scheduling and archiving of all the petabytes of historical data. You know, not only do you have to archive it, you gotta have a good way of retrieving it, you know, that doesn't take days. The newest NASA flagship telescope to be launched is the Nancy Grace Roman telescope, and that's under active systems refinement. They're undergoing preparations for launch. He's a cloud advisor for all of Space Telescope Institute. And they're going to be covering Grace as well. So anyway, I'll let him take it away.
Thank you. So I do work for us, the Space Telescope Science Institute, as a computer guy, not as an astrophysicist. I just happen to have a degree in the appropriate things, and that's what drew me there. But before this, I worked for the Medicare, Medicaid, and I worked for USGS as well. And so I've worked in many places because I'm a computer guy. At Space Telescope, we work with data from Hubble, Spitzer, Kepler, TESS, Webb. The next James Webb is under development, as was mentioned. We're working on the software to manage the petabytes of data that are going to stream down from that telescope. In approximately 5 years, they expect 60 petabytes or more of data because it is 100 times the view of Hubble. So if you took a Hubble picture and put a 10 by 10, that's about the size that the Roman telescope, which is Roman, is really the successor to Hubble. Some people think that James Webb is, but James Webb is more like a Spitzer replacement. Spitzer, I believe, was a infrared telescope, and so is James Webb. Whereas the Roman is going to cover more like the same wavelengths that Hubble covers. And what's really interesting to me is that the mother of Hubble, Nancy Grace Roman, gets the next telescope named after her, which is pretty cool. All right, I'm going to be talking about stars today. I could have talked about anything. If you don't want me to talk about that, you could raise your hand. I could just do questions and answers. But I have a prepared speech for the talk. Are there any before I get started?
Not yet.
All right.
I'll just,
But we will.
I'll just, yeah, they will. I'll just mention that we happen to have brand new Nancy Roman stickers in our door prizes tonight.
Okay. I did bring some James Webb stickers. They're in my bag. Okay. This is a different way to do a presentation. I don't have a PowerPoint. I just have images on my machine, and I'm using the Windows image viewer to show them on. And so if it doesn't work out, I won't do it again, but I just thought it might be interesting because then I could zoom if ever you want to see something in more detail. Or it's harder to do that in a PowerPoint. So stars. And all these images, by the way, I searched just on NASA.gov. So if you go to NASA.gov and search for stars and stuff, you'll find these images. Stars is what I'm going to talk about today. And this one happens to be a Halloween picture. Happens to look like a jack-o'-lantern. And so NASA posted this on Halloween one year. There's the moon, which is the same size in the sky. By chance, it's moving away from the Earth. We all saw the eclipse earlier. And then there's stars. And the sun is just a really close star. What does star mean? It's a little distracting to me. Can we turn down that echo?
Trying
Yeah.
for 5 minutes.
Turn down the echo. So, star comes from the word aster, and aster is a flower. When you look at a star in the sky, it has those diffraction spikes from our eyes. So our cornea isn't perfect, and we see these diffraction spikes, and so that people called it a star from this word. And aster is also the term from for astronomy. Astro is the lead for that. And there are many stars, and this is an example of diffraction spikes from Hubble. You can tell most of the telescopes apart by their diffraction spikes. So Hubble has these crossed ones, and James Webb will have 5. And it's just because of the design of the telescope, where all the different electronics are or structures in the way, causes these spikes. Just like your eye, if you hear people that say, I have night blindness, I can't see because all the lights are really pick up my field of view, that's their eyes having issues with diffraction spikes. Stars come in many sizes. And so this is Sirius, one of the brighter stars in the sky, and it has a little neighbor, which is a white dwarf. So the stars come in many sizes. That this here is about the size of the Earth for comparison. And there are big stars. So here is the Betelgeuse. At one time during its life, it was this big. And then that is the size of, I should use my my mouse. So at one time the star was this big, right here. And Earth's orbit is that small, and I'm going to move this because I can see that you guys can't see the entire image. So let me see if I can resize this. Come on, let me resize it. Let go. Snap. Yep. All right. What you're seeing here is, oh, it moved. Someone moved the screen.
I
as
did.
was adjusting.
I
Double
moved
adjusted.
it.
All right, so now on my screen, you can see the size of Jupiter's orbit right here. So at one time, Betelgeuse was way bigger than Jupiter's orbit. So if you put it in our solar system, it would swallow Jupiter and reach out and caress Saturn. So, but it's not that big right now. It's a little bit smaller than Jupiter's orbit. When stars get really big, they get very variable and change their size quite a lot. This is Eros, an asteroid, and I put this in here because again, asteroid has that aster sound in it again. That means star-like. And so when they first found these, they were tiny little specks in the sky that were moving that were star-like, but they weren't actual stars. And some of them can be looking like planets. This is Ceres. Looks like a planet, looks like Pluto. The reason why Pluto has been demoted is because there's too many. Well, at first, Ceres was a planet. It's been demoted to an asteroid because it's in the asteroid belt, because there were too many objects and they just couldn't have 100 things at the time that they were finding these be called planets. Planet just means wanderer, by the way, and some are robopods. And so this here is Deneb, I believe, and it is basically a big robopile, and it has this shape because while it's rotating, it can't conform to a sphere. It's too small and too loosely collected. All right, so that's the introduction portion. And now we're going to go. We're going to go on to talk about star life. You know, it's interesting how I have to stop sharing because this is in my way, so I can get the other piece going. And that's that. Oops. My presentation.
There seems to be a disease of that tonight, and I experienced it too.
Yeah, interesting.
Yeah.
Well, I can find it this way because there, I found it another way. All right, I'm going to go straight into the lifespan of stars. I heard that this is about 45 minutes. So I don't want to take up too much of your time. If you
Do not feel constrained that way. Just
Yeah.
give us your best. go.
it'll be more like an hour and a half if you want it to be.
Yeah. We want the full Monty.
Is that true?
You're not seeing the screen.
I didn't share it
You
yet.
can leave if you want, you know.
Oh, it's not up.
I have to share my screen again. So I got to pull back the presentation.
We do have little ones. I don't know what their time constraint is.
It won't let me share the screen. There's actually a technical glitch here that won't let me open. Let me
Try it again.
It's not your fault. I don't think it's your fault. This is the Zoom app. The Zoom application is displaying wonky. I might have to rejoin Zoom.
Okay.
I'm gonna see if I can get it this way. Maybe I shouldn't have.
While you're
I'm
doing
sure.
that, while you're doing that, question,
Yeah,
comparative size of Roman versus Hubble.
yeah. Telescopes are all the same size,
Okay,
but the image size is 100 times bigger in Rome.
It's
Now, it's to say that Hubble is less would be inappropriate because Hubble can see hundreds of times deeper. It's going to be a wider field.
okay.
It's going to see a lot more. And
Thank God we rescued it.
probably won't be run off of 386s to start.
you might think that's kind of weird that they do that. Okay, I found Zoom. I'm gonna.
How does that work?
So the reason they do that is because they've been hardened for space travel. There's a lot of so I'm quitting and I'm come back to Zoom. So I'm going to get back into Zoom. Can't wait to do it. It might have restart my Zoom. Share screen. Hey, that worked. Bring up my presentation. Take a couple seconds. There it is. All right. So there's a lot of cosmic rays out in outer space. Antimatter is out there. There's lots of fast-moving regular matter, and those are where cosmic rays are. And those slam into the electronics and can hurt it. And so they harden, they call it that, harden those electronics to work in outer space. And so a 486 is way better in outer space than your super fast, most optimal chip right now. It would crash too fast because it would get just corrupted too fast. And so there's a good reason for it, even though it sounds bad. Okay, stars can't form unless the gas is cold. Cold because things that are moving slow can join together. Think about it if you were in like on ice skates and you went towards someone really slow and you brought your arm, you could grab into their arm and then start rotating around each other, right? Pretty easy. But if you were careening down like those rollerbladers do really fast and you ran in, your arm would just fly apart, right? And that same thing happens when it's hot and fast. It just bounces off. It doesn't do anything. And when it's cold and slow, it can stick. And so we need cold. And here you can see a combination of cold and hot. So the background is hot and moving fast, and where stars have already formed, they're blowing it away and no more stars will form. But in those little dark blobs, they're so dense that it can form in there. And I'm just getting my nose in case I don't know what my images are about.
So it's outside for cold inside.
So here we have cold, dark blobs, and we have hot. And when I say hot, this could be 2 to 10,000 degrees. Whereas these cold ones can be below zero. They're very cold. And the coldness allows them to stick. Here's an example, the famous Orion Nebula, full of hot stars. They call it a trapezium. There's 4 stars in there, making a trapezoid. Those are very hot, large stars. And then there are a lot of little stars forming elsewhere in this. And here's another view of this famous. We use different wavelengths to find different details. The pretty pictures are for us, the common folk. I am actually a common folk. I am not a PhD. I don't do the research. I love these pictures. These are what my background. You can see them in the background right now, behind this presentation. Whereas the people who are doing the research, they want black and white images and they want graphs of data points. And so they can see more in black and white than we can see in these beautiful color images. I put in a few more here to show that we just have a lot of different nice pictures of outer space. Can you move my mouse for me? Is that what's happening?
No, that was my mouse making that pop-up go away. Sorry about
And
that.
then in the same constellation, Orion, the Orion Nebula is in the sword. It's the middle star in the sword. This is the leftmost star in the belt. And this is the famous Horsehead Nebula. Now another one to show you that. You can see the 3 stars in the belt here of Orion, and here is the leftmost star and the Horsehead Nebula. Again, in the dark is where stars are forming. They do not form where it's hot. And these have hundreds, if not thousands, of stars of gas available in them to make lots of stars. This is the famous, I rotated it so it fits on the screen. Normally you see it the other direction, but it would be smaller. This is the famous Towers of Creation from Hubble. And all these are Hubble, I'm going to show you. So James Webb gets all the glory, but I'm going to show you some nice James Webb. So some nice Hubble. So Hubble can take a picture similar to James Webb. It has infrared imagery that can see the cold, dark gas. And if we overlay those two, I big, I went too fast. My overlay picture went away. I don't know why it went away. But there's another one forming lots of stars. This is one of the biggest star forming regions in the area. It is the Tarantula Nebula in the Magellanic Clouds. It is about 160,000 light years away. Here's another star forming region. The reason I have this one in here is this star is diagonal. And it's right near a cocoon of other stars that have been formed. It could not get far enough away from the cloud because large stars die too fast. All right. Mass matters. And that's what I have here. This is mass that matters. So when you become a star, it's because you got more of the mass. If you're small, you become a planet. You also become rocky because you're so small, you can only hold on to the rocks. All the stuff that's light, like hydrogen, it's not water. Hydrogen leaves and goes away. But if you're big, like Jupiter, you can hold on to your hydrogen. So this is mostly hydrogen. It's not a failed star. Some people say Jupiter's a failed star. It would take 80 Jupiters to be a red dwarf star, a minimum of 80. That's just an estimate. And so it's just a very successful planet. 1 in a million. Put this here to try to give you an idea of what a million looks like. And this is only 7,000. So the Earth is a millionth the size of the sun. So it takes a lot to make a star. A lot of mass. It comes from these clouds. These clouds up there, this is called aerogel. It's called liquid solid smoke, if you ever heard that. It's made of silicon and it is light as air, pretty much. If you had a vehicle made out of this stuff, you could pick it up by your hands, but because it's so fragile, you'd break it in half when you lift it up, just like a superhero does. When they pick up those cars and break it. That's how light it is. This is many times denser than these clouds. It takes a long time for these clouds to come down and make stars. Here is the Angel Nebula making stars. This is a James Webb picture. This was actually the James Webb first-year anniversary picture. I have a poster for whomever. That is that galaxy, nebula. And that, when you talk a lot, sometimes you can say the wrong word. And I just said galaxy instead of nebula. If you catch me, call out and I'll correct it. Again, here is another nebula forming stars. This is, again, the Tarantula Nebula. Most stars, on the order of 50%, make binaries. So that basically, I said mass matters. Sometimes two stars share the mass in an area and they start orbiting each other. So Jupiter, had it been about 100 to 1,000 times bigger, it would have to be 1,000 times bigger, by the way, to be equal to the sun. They would orbit each other like siblings. Difficult for planets to form around there because they're churning up the area. You can see it's very violent in there. I'm going backwards on accident, press the wrong button. Some stars form in large fluxions. There are things called the globular clusters. You probably looked at them with your telescopes being here. And globular clusters have lots of stars in them. And the old stars are red and the new stars are blue. Blue stars are hotter stars. We are used to blue being cold on our planet because ice is cold and it's blue. And people, when they get cold, their lips turn blue or their skin turns blue. We're used to blue being cold. Actually, blue is hot in outer space. And red is cold. And I have a graph to show that later. Here we have the different size of stars. So we have or objects in our space with stars. So the sun is this big. We have a low mass star. This is like a red giant, a red dwarf. And there's a brown dwarf. And then Jupiter. Notice that Jupiter, if it was 80 times more massive, would only be a little bit, possibly even a little bit smaller. Because when more mass piles on, the gravity pulls it in stronger. So there's a little contrary problem. So mass matters. So the more mass you have, the better the star you make. Here's another example of the same. There are classifications of stars, and they didn't know when they were making the classifications of stars which star was what. If they did have a priori knowledge, they probably would have said A, B, C, D, E, F, G. Well, if you look in here, there is an A, there is a B, and there's a C, but you don't see it in the list. Well, when they figured out after classifying all the stars, they put them in order of their size. So you got M, K, G, F, A, B, O. And so they classified them by their spectrum, how bright they were, and what their brightest light was. So the big stars, they're on the order of like 10 to 100 times bigger than the sun, will give off most of their light in the blue. They're also called ultraviolet stars because they actually give off so much ultraviolet that it's more than the blue. There are B stars, A stars, and our sun is a G star. I'm pretty sure it's a high mass G star. Our sun is actually mostly white, but we think of it as yellow because of the sky taking away the blue. So our sky is blue because of scattering, and some of you may have known about this, that our sky is blue because of the scattering of sunlight. But if the sky is blue, down the way, when we look at the sun, we've got blue taken out. If you take blue out of white light, you get yellow. So the sun is actually very close to being white, even though here it's a little exaggerated to make a point of the different stars. Here is a plot, and I'm going to help you make sense of this plot. So down here, we have 3,000 degrees Kelvin. 3,000 degrees Kelvin, it doesn't matter when you're talking this hot, if it's Fahrenheit or Kelvin, because it's about the same. 3,000 degrees Kelvin makes a red star. That is a red dwarf. 4,000, or excuse me, a brown dwarf. Then we have a red dwarf, and then we have the average star, like our sun. Our sun is actually 5,700 Kelvin, almost 6,000 Kelvin, almost 6,000. And if you take these two lines and you put a curve right in here, the highest point would be in the green. Our sun is actually a green star. But because it's so flat, notice how some of these are even more flat. In the red, they're more flat down here. In the red, they're very red stars. When you're flat in the green, our eyes perceive that as white. So the most light it gives off is green, but because it's such a tiny amount extra in the green, we see it as a white star if we were not on the planet Earth. It's our atmosphere that makes it look yellow. I put this one in here because it's fun. This is the James Webb Space Telescope picture. We can tell because we have the 5 or 6, what's that, 6 stars, 6 plus the cross. So the 6 are caused by the fact that it's hexagonal mirrors. And the cross in there, this extra cross, is because there's support beams holding up the camera. Holding up the mirror that points it the light back down into the camera. James Webb took this picture after Hubble took this picture, and it can see through gravitational lensing one of the first stars, oldest stars that we can possibly see. The star is probably something on the order of 28 billion years old, away and old, but the universe, away, 28 billion light years away. The universe is only about 14 billion years old, and those sound like a contradiction, but the universe is expanding and making things farther away. It was probably born in the first billion years of the universe. And it's a quirk of fate, but the universe is huge, so there's lots of quirks that can happen, where the magnification of all the different gravitational effects in this cluster made a star, a single star show up. And using spectral analysis, not this image, but the graphs, there are two humps. There's a bright hump and then there's another hump. And those two bumps mean there are two stars there. There are likely two stars. There's probably a big giant star and a companion that's much smaller. Hubble couldn't see that because it didn't have the same wavelengths of sensitivity that James Webb has. Stars form and make solar systems. These are a bunch of little collections of Hubble's views of different solar system forming areas. All this dust around the star can become planets around them. Going back to the Orion, which is why I included the Orion earlier, we can actually see that these come from the Orion Nebula. There are stars forming solar systems over there. And zooming into those solar systems, you can see that they're fuzzy little disks, fuzzy little disks. James Webb, not to be outdone by Hubble. This is the James Webb picture of the Hubble, and I wanted to show this one because if I toggle between two pictures from James Webb, something stays the same. It's there. Can you see what stays the same? Bright star. The bright star in the center, yeah. What else? You see that red in the background? This, I'm gonna move my mouse now. Look in this area. Whoops, that's another James Webb picture. Okay, so back and forth. Kind of like the optometrist, right? A or B. All right, what's happening here is that star that's forming there is new. It's turning on. And this is the beginning of a star. So stars, when they first turn on, stuff is falling in and making things hot. And you can feel that same heat by rubbing your hands together. That heat you feel from rubbing your hands together is the exact same heat that ignites a star. Just like you take a stick and make a fire, stars do the same thing, although they become millions of degrees through this process. So this is called a protostar, and it's shooting out material as it turns on. Here's another star turning on. This is a baby star. The star is probably only 1 million years old, and in 1 million years, it'll be a full-blown star. If we could zoom in on this, which I should be able to using the Of course, things don't work when you want them, right?
Down at the bottom, the magnifying glasses.
Right now, but I should be able to pinch zoom because I'm in the app that lets me do that. And what's happening is the presentation is getting on that. I don't want to stop shooting. Why is I'll get it. Not letting me zoom in. It changed the mode. All right, so this one is another one. This is another James Webb picture. I don't have to zoom on this one. In the very center, you can see the dust disk and the star turned on. And the reason it shoots out in two directions is magnetic fields. I heard a discussion about magnetic fields being detected for the coronal mass ejections that reach us to make the northern lights. These are the magnetic fields of that star that's turning on, channeling the expel of material as the star turns on. Yeah. All right. This is the Eta Carina Nebula. And Hubble took many pictures, and James Webb took some too, of this area. And it's lots of stuff going on. You may have remembered this picture from earlier when I had the hand holding the block of solid smoke. We've got a star that's in some throes of explosive energy. And then we have star forming regions on the top, these are, again, new forming stars. And this picture here is up here in this corner. And I'm going to now advance, and we're going to look at each one. So here is my background screen. I use this as my background currently for my computer. I just love this picture. It's a Hubble picture. It's one of my favorites. This is the Eta Carina Nebula. And right here, this bright dot here is that exploding star. Down here in this area is the place where I said solid smoke and showed you that image earlier. Over here is the majestic mountain. And I'll show you those in a bit. This nebula is so big that the James Webb picture isn't even in this space. So here are the majestic mountains. We got lots of stars forming. So we have stars turning on here, baby stars. These are all baby stars turning on. And this is what it looks like when we can see through the dust and gas that's illuminated and see deeper into that cold, dark gas. And then the combination, again, that was Hubble. And here is Eta Carina from James Webb. This was an early picture from James Webb within the, I think it was released on the July 12th, 2022. A very early picture showing the power of James Webb. We can see it's James Webb because of all the different spikes. What we have here are blue stars that have turned on and they're pushing that gas down. This cold gas is still forming stars. And any one of these nodules, this is a big one, but there are lots of little ones that people look at when they're doing their research. You can see another nodule. I'll move my mouse if I can. Down here, here's another nodule right here. These are little baby solar systems. Again, new stars forming from cold, dense gas.
Can I ask you a question?
Yeah.
So you're saying on the previous picture
Yeah, I'll go back.
that gas was all up there, and when those stars started to form, they actually pushed that gas down, that brownish we see?
Yes. Yes, it did. It pushed it using their solar wind. So we have a solar wind too from our sun. Yep. And so the solar winds from all these stars up there are pushing or blowing. You think of it like literally blowing out candle and pushing that gas away. And it looks like down, but there's no down in our space. So if I go back, I'm going to go back to that overview. We're talking, it's way up here in this area, and it's vertical in this shot. So you can see how that elongated picture that was rotated to fit, which is this picture that I was zooming in on, is actually pushing, you could say it's pushing sideways.
Is it just blowing that into space, or is it congealing?
So they are just blowing stuff away from themselves. And then the mutual gravity of each of the different stars that are forming are holding on to some of that material. Yep. Yeah.
When we think about high pressure, low pressure, heat, cold, high pressure expands, cold contracts.
Yeah.
So when you're talking about a void-like space, the radiation would be particulate, I guess, and as that particulate expands from the shortwave radiation expands into long wave, and then it expands. And re-emits as long wave, then what's causing the wind then?
So the star is fusing, the stars that turn on start fusing, and we'll get to that in some later pictures. And the energy that they have pushes outwards. They give energy to particles that move fast. So think about if you have a hot air balloon, right? And we have the fire underneath. The fire underneath the hot air balloon makes it expand and become big, and then it can lift off the earth. And then by the temperature and the amount of gas they put in there. So, but they're trapping it, right? But in outer space, there's no trap. And so it's just blowing away.
It's a void, so there is dust throughout that obviously we have globules of dust.
Yeah.
That are cold. But there's still some matter out in between beyond the void of that dust cloud.
Yes.
That is heating and cooling, and those are pushing through, and that's your solar wind. It's actually particulate that's traveling through space.
Yes, and most of those particulates are just hydrogen atoms. Most of it is just hydrogen.
So, okay.
Yeah, but it is still.
It's a gas.
It's still a gas.
Gaseous wind.
Gaseous wind is moving, maybe sometimes 200 kilometers per second, maybe it's moving at 20 kilometers per second. but it's still moving out, and it moves out because it was close to the star at one point. And the things that were gonna move into the star stay with the star, the things that move away from the star keep moving away from the star. And so it moves out in a way. If it didn't move out in a way, it's staying in the star. So you're seeing stuff that is moving up in the direction away from the star. When I say seeing, these, you can actually see, I'm gonna move my mouse here so that if people are watching online, you can see these tracks coming through here of this, of the wind of those other stars pushing down on this gas. And I call it gas, but astronomers, when they're doing the research, they call it dust. So if you hear me say dust and gas back out there are the same thing for the most part, but they call it dust because it's cold, not hot.
So it's gas, it's not particulate.
It is not, it's not something you can put your hand on. It's something that you, like a fog that you move your hand in. In fact, when you look out in the mountains here in Maryland,
It's.
and on like a day where the sun is rising and you see the fog, that's thicker. That fog is thicker than this fog, even though this looks denser. The reason it's dense is we've got light years of material, not just a couple 10 miles, say, of material. So we have light years of material. It's very loose. It's very,
Like 1,000.
But it's not material, it's gas,
but it is a gas.
but it's not material.
Well,
Gas has mass.
gas is a material, but you're not wrong. It's just a matter of semantics.
It's like
Right.
that.
Almost every element, when it goes down to, absolute zero, is a solid. Or a liquid, so technically, yeah, it could be considered mass.
Well, it is mass.
Yeah.
Yep, it's matter. And a gas is matter, but we think of like here in the room is oxygen and nitrogen, right? Mostly oxygen and nitrogen. And that's a gas. And that is exactly what's out here. Instead, in fact, I don't know which ones it is, but some of those molecules that are glowing are oxygen. I don't know which one it is. It could be the blue, it depends on how they colorized it. When they colorize it, they make it for our eyes to look pretty. And then you have to reconstruct the description on every picture to see what color corresponds to what gas, because they didn't make a color always blue for oxygen, say, or always green for oxygen. They make it look pretty, so that we can see. Here's another piece of that same nebula. We call this the keyhole. And you can see up here in the top, right here, this is another little nodule of a solar system forming, another star. This is that, I want to call it exploding star, but I'm pretty sure this star is not actually exploding yet. It's about to. When an astronomer says it's about to, it's probably going to explode in 1,000,000 years. I mean, something outside of our comprehension, but less than universe time scales. It is about to. This is if you do a search on Edda Karina, you'll get this a lot, this picture a lot. It's so famous, they mapped it in 3D. And so here you can see what it looks like if you rotated it around and look in the backside. I think that's my last picture in this. This is formation of stars. Now we're going to talk about the life of stars. How they live, and then we'll go into how they die. And
Just, we showed the 3D NASA clip of the pillars of creation at the beginning of the What's Up.
awesome. Stars. All right. Now we're going to talk about stars and their lifespan. Let's see if can I zoom again? Yeah, I can zoom again. All right, so this is the sun during a coronal mass ejection up here. And to give you a size comparison to the Earth, that little speck that I had to put the word Earth next to is how big the Earth is compared to the sun. The sun is 333,000 Earths in mass, but it's 1,000,000 times bigger. And the reason it's 1,000,000 times bigger is because it's 1,000,000 times hotter. In the center of the sun, it's about 15 million degrees. And what keeps a star burning, and we use that term loosely because it's fusion, it's not like burning a campfire, is the core is hot and that pushing out I told you about just earlier, when we're talking about the gas and pushing out, that pushing out is balancing gravity. And the size of the star is actually determined by its mass. The size, the mass pushes in, creating temperature in the center by the same friction I told you about, rubbing your hands together, heats it up in the center, and then when it ignites and goes into a fusion burning phase, which is just like a nuclear bomb going off all the time, holds it up because the heat makes the molecules move faster, expanding it. If you ever want to try this, take a milk jug and put it outside in a cold winter day. An empty milk jug that's all done, and cap it. Then bring it in the house near some kind of warmth. It will expand and pop out those little dented rings because it's expanding because it's getting hot. And so the sun expands to as far as it can, given its size. It can't get bigger until it gets hotter. Can't get hotter unless it gets more mass or it gets close to its dying. Little stars, I want to go back. The sun is only making energy in the central 1% of the star. This might be a little bit too big. I think it actually is drawn too big. Only 1% of the sun is actually fusing and making energy. It's 1/3 of its mass, but it's only 1% of its volume. And all stars pretty much go like this. If it's a bigger star, it's a slightly bigger center, except for red dwarfs. Red dwarfs are basically the core of a star with nothing else on the outside. And they're 1/3 to maybe half the mass of the sun. And they can fuse their entire star's worth of material. So they can last longer because they can use all the material, not just the core. They're dangerous for planets because their coronal mass ejections happen more often because it's the entire core sitting there, and the planets end up being closer because they're a tiny star. The reason why the sun doesn't just burn out is because things can't get out right away. And so here we can see, this might be an animation. Yep. So here we can see, this is a NASA animation of the trajectory that light takes, energy takes getting out of the sun. Sun actually doesn't expel its energy from the center out to us. It takes between 10,000 and 1,000,000 years for the energy in the center to get to the edge. And then it comes out to us in about 8 minutes. And I'm talking about the light. I'm not talking about the coronal mass ejections that were talked about earlier. It's hot in the center of the sun. Some people say that the lightning bolt star is hot at the center of the sun. No, I think it's about 10,000 degrees. Forest fires, they can get really hot. No, not that hot. Not that hot. That's radioactivity. That's fission. No, not that hot. It gets so here's fission where things fall apart. You got technetium turning into calcium and then giving off some energy. That's not what the sun does either. It does fusion. It makes things bigger. So we got 2 at the top, 2 hydrogens. They're protons. They merge and make heavy hydrogen. It's called deuterium, just so we have a name for it. But it's dew, meaning 2, and irium, because they keep wanting to call all the different elements with some cute little last end name. I don't know if you guys know about aluminum versus aluminium. That's because the Europeans like that ending. So they change the pronunciation. All right, so then after it makes this, it's easier for these 2 to come together to make helium-3. Helium-3 is 2 protons and 1 neutron. And the reason it's easier for this is because this one is heavier. And we all know that heavier things have more energy. And then when it makes those, the sun collides two helium-3s together, makes helium-4, which is this bottom one, and then gives off two of the hydrogens that were superfluous in that whole mixture. Because we had 6, it only wants 4. One of the most stable nuclei in the universe is helium. It gives us the most energy differential after this is done. And that's what the sun does. And it takes, I have this written down so I can tell you guys. It's quite fascinating. It takes 1 in, where it says, 1 to 3.5 quintillion against that it's going to form this. Yes.
Just choosing postcon.
Oh, I only wanted to, yeah, I only wanted to give off, give the core information. Yeah, there's also neutrinos being given off like crazy here too. Every one of these reactions gives off neutrinos. And so 1 in 3.5 quintillion against. What does that mean? That means that for every time one of these things happens, it doesn't, when they come close, you have to roll the dice 3.5 times 10 to the 18. That means 18 zeros, 3.5 with 17 zeros. You have to roll the dice that many times before it'll connect, which means that it takes 5 billion years for any one of these things to happen, which is why we know the sun is 5 billion years old, because half of it's gone, half of it is used up. Therefore, if we know the odds, we know how old the sun is. It's a random path. I just put this here. This is Curiosity or one of the other probe things roving around Mars. I put this here to show that it takes the easiest path. So the reason why we went this path is we went the easiest path to get up the hill. We didn't take the straight up path. And some of it's interesting, but I just put that here for a cute little demonstration of taking the easiest road. Where does the energy come from? We all know who this is, right? Albert Einstein. This is him later in life. While he was doing all his really good work, he looked at this. That's him in the patent clerk making his E equals mc squared. The reason is that mass is energy. It's not that mass can be turned into energy. It's not that energy can be turned into mass, which in a way they can. Mass is energy. And because we give up some mass when we connect those protons together and make helium, we get energy. E equals mc squared. Powers the sun. Only, now here we want hot gas. I put this in here to say, we want to make stars with cold gas that move slow. Now we want it to move fast because we have gravity to hold together. We want it to move fast so that it can bombard and make those protons combine and make helium. Again, another picture saying it's not this hot. It's hotter than that. Now, I found a picture that had some mountains and I constructed this out of it. And this is supposed to represent one of those proton neutron deuterium. And here comes another proton. And it wants to get in there. And if it only has that much energy to get that high, it can't get in. And the sun is not hot enough for it to go over the top. But quantum mechanics comes into play and it tunnels. And that's why I put a little shovel there. It literally jumps the rails and gets in and makes the element. It doesn't go over the top. It goes through the barrier and makes these things. If quantum mechanics didn't exist, the sun would not be able to shine. And it is very old. This is just a little picture I found on NASA's website to say the sun is 5 billion years old. And it takes 5 billion years for a 50-50 chance for any of those protons to make helium. Again, the larger stars, there's only a few, by the way. There's only a few percent, less than a few percent of stars that are gargantuan, like that big blue one in the background. By the way, there's a picture like this when I was a kid that may be interested in this science. I didn't even notice the blue arc. I was looking at the other stars and saying, oh my gosh, they're so much bigger. And then I realized this big arc is another star. They are like 100 to 300 times the mass of the sun. And they are so big, the biggest ones could swallow Saturn. And they burn faster. And here is a red dwarf. Red dwarfs are the most common star out there. More than 80% of stars are red dwarfs, and they're very hard to spot. We can't see any with our naked eye. All the stars you see out in the night sky are on the order of 10 times the mass of the sun. And here is a Wolf-Rayet star. This is a star that is gargantuan, so big that, and so violent that it throws off layers upon layers of itself. When stars explode, they can make more elements. And so I just mentioned our sun is making helium. Our sun will stop making elements at carbon, but we know there's gold and there's mercury and there's silver out there. Other stars make the larger elements. However, during the lifespan of a star, it can't make anything more than iron. I think I have another picture of that. Where did I put that picture? Sorry, I'm jumping around, but okay, here. Is it gonna do it? Okay. We have these little layers in the star. And at every layer in the core of a star, it makes different elements because it gets hotter and hotter and hotter as the star gets older. It gets hotter because as it stops burning, and again, it's fusion, it's not fire. As it starts finishes fusing the core of protons or hydrogen into helium, it runs out. And therefore, it's going to cool off a little bit. That cooling off then allows it to shrink and then it heats up until it can do more. Remember I said there's a balance there. And so as it grows, burns and ages, it makes different elements. Here we go. And the larger stars can make, in their outer edges, can make helium, and then they can make carbon and oxygen, which is the sun will stop there. But then we can turn carbon into neon and magnesium and silicon. And we can make silicon into iron. Iron is the end of the road. Iron is ash for stars. You might not think that because it's iron. It's kind of weird. Nothing can be combined after you got iron to make more energy because it's the end of the road. It's like being at the bottom of a hill. You can't get more energy out of your bike at the bottom of the hill. You have to put energy in to go back up. So once it makes that, after a few seconds, it's so cold and so dense in the center, just after a few seconds, maybe a couple of minutes, after millions and billions of years, these stars all of a sudden collapse on themselves. Because as I mentioned, it collapses until it makes more heat to make more new stuff. And what happens in the last seconds is that it makes a little bit of iron and then rebounds and makes elements. This here is how much energy is given off as it makes things. And you can see that iron is at the top of the curve. Use my mouse for people online. Right here, iron is at the top of the curve, and everything is not going to give you any more energy. This is a graph showing how much energy is given off each reaction.
What's the U over on the far side here?
Uranium. It's uranium over there.
Yeah, no, uranium's created, right?
Only during the death of stars, and we'll get into that when we talk about death. This here is the classification of stars. Now I'm going to show you. Take that field of stars, and if we organize them by their brightness and then by their color, this is the animation made by NASA to show that first we're doing color, and then it's going to organize them by their brightness, and you're going to see that there is a trend of hotter blue, colder red, and the brightness goes up, and the last part there is that red tail on the other side is the giant stage, red giant stage.
That like the life cycle then too, right?
This is called the main sequence. So this curve, I can't stop the animation. It's a GIF, but when you see this diagonal, that's called the main sequence. This diagonal is the main sequence, and then as they die, they go up to the top right. The stars that are blue stay on the top and just move around on the top.
Thank you.
Yeah. So that's the life of stars. Now we're gonna talk about the death of stars, unless we are at our saturation.
No, we're not.
Glad you're coming back.
All right, so now this is the life cycle of stars. So we just talked about the formation and then the lifespan of stars. Now we're gonna talk about the death of stars, looking at this cycle. So we have that formation in the cold nebula. You cold the stars. If it's gonna be a sun-like star, it's just gonna make a protostar, make a sun. It's gonna last for a few billion years. Ours will last about 10. We're 5 billion through. It'll grow to be a red giant. As the hydrogen runs out, it crushes down, makes it hotter. And by a quirk of fate, because the core is hotter, the outside can expand out, and expanding gas cools off. So even though the center is much hotter, the outside becomes cooler and larger. And then it makes a planetary nebula at the end, and it makes a white dwarf after that. And the phases are a few hundred million years to make the star, between 5 and 10 billion years to live, a few million years as a red giant, maybe a billion, and then 10,000 years of this expansion. So you see here, and then there's this arc that lasts about 10,000 years, maybe 20, and then the white dwarf, our sun will turn to white dwarf. That can last 1 trillion years. It's just a nugget of hot that has nothing to do. And there's really, you think of cold of outer space, outer space is cold. For a star, there isn't anywhere to put its energy. It can only give it off in light. And so it sits there at billions of degrees for, millions of degrees for on the order of 1 trillion years, which is quite crazy. That means all white dwarfs that are out there are still white dwarfs today and were from the beginning of the first white dwarf. If they're bigger, they become massive stars, supermassive, super red giants. They explode with a supernova and become a neutron star or a black hole. And the difference there is on the order of 10 times the mass of the sun. So anything under the 10 times the mass of the sun will probably become a neutron star. Anything over 10 times the mass of the sun will become a black hole. Yeah.
Question. What about hypergiant? Is that bigger?
Hypergiant is something like those stars I showed at the beginning that are so big that they take up like the orbit of Saturn. Yeah.
Can you go back to your previous screen there?
Yeah.
Okay, so this screen, Jack, are you getting listening?
Yeah.
All right. So this incorporates all of the possibilities as far as star formation and life cycle of stars.
In a very
all-encompassing view of what's possible out
a
there.
10,000 foot view, so to speak. Right?
Either a massive star or a sun-like star.
So 80% of stars, the sun is approximately bigger than 95 to 97% of all other stars. Okay, so that's why we talk about the sun-like star cycle. Because it's, even though there's no average, nothing is average, but there's an average, right? You ever hear that term?
Yeah.
If you take the average person, you can't find them, but there's an average of people. Well, there's an average of stars, and the sun is kind of average. Now it's weird because 95% of other stars are smaller, but yes, it will do this type of thing. If it's smaller and it doesn't become a white dwarf, it'll become a black dwarf. It'll just cool off and turn into something black instead of white. But yes, in general, you have sun-like stars and bigger than sun-like stars. Yep.
Let me ask, so how old, is this still a theory or is this proven?
Well,
Looking at the empirical data,
yep,
it's proven, right?
correct. Now, in science, we never actually can prove anything. We can just refute
right.
and things that are not just proven yet.
Right.
And so just to be careful.
Right.
There's nothing to.
So in terms of where we were
when we humanoids arrived at this as a sort of all-encompassing theory, what year are we talking about?
Oh, maybe only 50 years ago or less.
50.
On the order of 50 years, yeah, including plate tectonics. Plate tectonics in our lifetime.
1930s.
Yeah, it was invented in the 30s, but it wasn't accepted until maybe the 80s or the 60s. Plate tectonics is really new too. All modern science is only about 100 years old.
Right.
Yeah, so the turn of the century, 1900s, is when everything changed and we started rapidly gaining information. So all this information is very young. We live in an amazing time to know all this.
We do.
We do not expect any of this to be overturned in any substantial way, just refinements. So would a black hole form if it was 9 suns, or would it be 11 suns? But we say 10 because it's a nice even number to use.
Now, do we understand the mechanisms about whether a massive star would become a neutron star, a black hole, or a supernova?
We do, but there's nuance. So there's always people doing research to get even more, like I said, nuance on there. We do. So we know that a black hole forms because the neutron star that would form had too much more material fall on it from the out before the explosion happened. And if too much falls in and crushes it just a little bit more, it becomes a black hole, and then there's no escape from there. But if the explosion, we're talking on the edges, like maybe if it was 12 or 13 masses of the sun, then if the explosion happened early enough before it reached what's called the Schwarzschild radius, then it could blow that away and stay a neutron star. Also, spinning has a difference. So if a really slow spinning star collapses down, it might become a black hole. But if a really fast spinning star falls down, it starts spinning 700 times a minute, second. I think it might be a second. I think they spin some of them 700 times a second because they came from this big star, and that spinning can actually allow a larger neutron star to form. And we know all these different things from the math and from observations, confirmation from observations. We can't do any experiments, right? The one downfall of astronomy is that there's no experiment we can do to prove these things, because the star takes 1 billion years to run, right? Or a star forms in 100 million years. You can't run that experiment. You can just look at this one and that one and this one and get general patterns. But to answer your question one more time,
yeah,
I don't believe there's anything that's going to refute, but maybe refine.
Right.
Just refine. Yeah.
That's a great graphic right there, by the way.
And again, if you search for this on NASA's website, you'll eventually come across it. I got these all. This is an iron meteorite on Mars, I believe. And I've put this here because we love iron. We think of it as a great material, but it's the death of a star. We can tell the inner cores of stars what they look like, just like we can with the Earth. So this is the Earth and Mars and the Moon, and with seismic material data, we can see what the center of the Earth looks like, what Mars looks like, and what the Moon looks like. So we can do the same thing with the sun, with its quakes and such. We actually can use sonic information, sound information, which no sound travels, but we can see the ripples in the sun, and they can actually see the can't say sunspots on the backside of the sun before they even come around the edge with some of that information. This is a pile of carbon. Our sun will stop at carbon, I mentioned, before it dies. This is the star in its death throes. Looks very similar to a star when it's forming, right? But we also talk about how humans, we start out as babies and we stop, and we have diapers on, and then we die. Just before we die, we need diapers. So stars, likewise, in the beginning of their life, they look very similar to the end of their life. And again, magnetic fields channels this information. There's another view of the same butterfly nebula. Another view, different wavelengths. And this one here, I put in here, this is not a star exploding. This is probably a star that absorbed another star and just gave off a little burp. It just ate one for lunch. There's a chance it was something maybe a super Jupiter or a small red dwarf. What happened was it spun around and spiraled into the star and stirred it up and made a little burp of activity. And the reason this is interesting is this is the light, not the gas. The light is coming off the star and illuminating the fog around it. Kind of like if someone turns on the headlights in the fog. Oh, now I can see that it's foggy because I can see the glow around the headlights. Well, space is so big over several different pictures taken over approximately 2 years. We can see the gas in the outer space being lit up by the star. Notice that you can't see it until the light gets there. So it's dark on the edges and it becomes bright on the edges. I put this in here to show you that there's gas and stuff to make stars all over the place, even if we can't see it. When it's really cold, you can't see it. It's also a neat picture.
So let me ask you this.
Yeah.
Are the optics, do they have to be cleaned on the Hubble?
We can't clean it.
It doesn't have a windshield.
It does not, but it does have a door. We have a door on the Hubble.
Right.
And if we think that there's some debris coming, like, that could hurt Hubble, make it dirty, we close the lid and then open it up again.
Have you noticed any, accumulation on the lenses of the?
We have noticed on James Webb, because it doesn't have a tube, it's just a lens out there in the air, in the void of space. We've noticed it getting dirty already.
Really?
Yep.
And what do you expect that to be carbon, that's carbon?
It is little carbon meteorites that are hitting it, and actually more so than dirtying it, they crack it a little bit than dirtying it. But it's like getting your windshield, like a little ding, we get to call the people that put the goop in there to fix your windshield, you know, when you did a spider web before spider web's out. But we can't go out there and fix it. It's a million miles away. And we don't have a space shuttle anymore to fix Hubble either.
Has anybody done a surface wipe of anything that's out, say satellites or anything in return?
They did on the space station, and they found bacteria and stuff growing on the outside of the space station. So they have. Yep.
They have done.
Yep. And that's pretty amazing, because that's the void of space, and
Right.
we found bacteria growing out there.
Wow.
So, yep. This here is a star that's on its way out. It's called Wolf-Rayet star again. It's blowing out material on its death throes, and another star is orbiting it. This is a James Webb picture, and the other star is carving out a line every time it goes past. But because it's throwing out material, just like waves on a boat, the material is moving out, and the other star is carving a trail, and then the ripples keep moving outwards. So we know there's two stars.
Vibrating.
What was that?
It almost looks like there's like a vibration of light within those ripples.
It does look that way, and because of different outbursts, I don't know exactly why for sure, but that's why it's not perfectly circular. We have dead areas. You have a question?
How many times do the waves go out?
I think it's 18. I think it's 18 rings.
Not like, is it all the time?
Oh, yeah, it's constantly doing this, probably for billions of years, probably from.
Second.
Oh, so every rotation is approximately, don't quote me, but I think it's 25 years. So it's a 25-year cycle.
So each ring is 25 years.
Yeah. Pretty sure it's 25 years. The star comes in to the other star about 1 AU, 1 Earth distance away, and goes back out to something like Saturn and comes back. And we're seeing every 25-year cycle process. I'm pretty sure it's 25. It might be 28. I never had to memorize those numbers precisely because it's difficult. This is the Crab Nebula. And I heard you mention M something earlier today.
M20, yeah, M57.
M57, this is M1. M1, I put this in here because this is the one that made Meissner say, is that a comet? Oh, no, it's a nebula. Oh, darn it. I'm gonna write that down. M1. He didn't say M1, he said 1. Then we later said M because it's Meissner.
Messier.
Messier, sorry, thank you, sorry.
Just had to say
That's right.
something.
Thank you for correcting me, because I make this. Yeah, well, Messier made made that mistake. He said, I might make a mistake again. And so his 100 items, or give or take, are because he didn't want to make that mistake again. And this is the first one. Crab Nebula exploded likely in 1054 AD, recorded by the Chinese and recorded by people in the Pueblo of United States. There's a handprint and a crescent moon or something like that, and guest star. And we can pretty much put it in the same time frame. There's another view of many wavelengths. So if we get more wavelengths of light, we can get more information. And so we're seeing visible light, we're seeing infrared, we're seeing X-rays and gamma rays. And I'm pretty sure that the center swirl is the X-rays. I don't know where the gamma rays are. And this was an exploded star that became a neutron star, and it's spinning around several times a second. Don't remember the exact count. And it's making that disk as it spins around, and it also has a jet coming out here. I'll push the mouse here. There's the jet coming out here, and there are animated versions of this somewhere on NASA. I couldn't find it for this time. Here is another exploded star. This is called a Type 1a supernova. Type 1a is when two stars are orbiting each other, and the smaller star, usually a white dwarf, orbiting a larger star, accumulates matter, and then explodes. And it explodes because it can no longer be a white dwarf. It's too massive. And they don't always, but very nearly they do, explode with the same brightness. But if the brightness is brighter, it lasts longer. If the brightness is less, it lasts shorter, and it's predictable. There's a graph that the astronomers have, and they can pinpoint its distance based on that brightness. That's how we figure out how big the universe is. Again, that same picture from earlier, we have an exploded star. The star is actually not fully exploded. This is one phase of its explosion, and it can explode again. But big stars don't last very long. They can't get far away from their nebula. The sun is very far from its nebula. We don't know where our nebula was. We don't know where our daughter stars are. Our siblings are lost to time because our sun can last so long. But when you can only last like 10 to 100 million years, you just drift a little bit away from your cloud that you formed. 1987 was explosion 170,000 light years away, very similar to that other nebula I said, called the Tarantula Nebula. It's near, in the same vicinity. This star exploded, and with James Webb and Hubble, we've been tracking its exploding radius. Most of this is energy being given off and illuminating gas around it, but you can see in the center here the explosion of the star. This star exploded, and as it collapsed, the explosion was as if the sun burned everything in less than a second. But it literally made as much energy during that as the sun's entire lifespan, and gave off the same number of neutrinos. Going back to your extra particles, it gave off the same number of neutrinos the sun would give off in its lifespan. Neutrinos pass through you to the tune of something like 1 trillion per second, coming from the sun, coming from outer space, and do nothing to you. You might in your lifetime get a little glint of light once, and if your eyes are open and it's bright during that day, you're not even going to notice it. If you're sleeping, you wouldn't notice it. You're not going to notice it. Just, I'll tell you that. It's that few times that it collides, but because it's 10 billion years of the sun's burning, glowing neutrinos given off in that fraction of a second, it tears apart the star. So exploding stars of the largest magnitude are neutrino bombs. So neutrinos, they're tiny little particles, but there's so many of them, it tears apart the star. This is the lifespan of it from 94 in 2003 from Hubble. This is basically, there was debris given off. Remember I said that blue one just a bit ago exploded a little bit, and it's gonna explode again. It's illuminating the prior ejections of matter. That star in the Crab Nebula that I said is spinning tens of times a second, maybe hundreds of times a second, is a neutron star. They become the size of a city, and they become the mass of approximately two suns, maybe 2.4 suns. That's how big they can be. And they become the size of a city, so the size of Baltimore. And you've got the mass of two suns. Just a little bit smaller, and it's a black hole. It is right outside the edge of being a black hole. Not much smaller than that. This is a white dwarf, very similar. Excuse me, that can't be a white dwarf. White dwarfs are the size of the Earth. This can't be a picture of white dwarf. I put it in there because I thought when I saw its whiteness. This is another image of another view. Magnetars are another type of neutron star. So if the star has a lot of magnetism as it dies, when it becomes smaller, it magnifies because it's crushing down that magnetic field into a smaller area. Just like I said, it spins up faster if it's spinning a little bit fast. Just like the ice skater who pulls their arms in, they spin super fast. This thing spins fast, and it has a tight magnetic field. And pulsars are when the debris and light coming out of the magnetic field point to us. We see it as a beacon. The beacon, as you notice, I'm going to go back there, does not have to line up with its rotation. It doesn't have to be on its poles. It doesn't have to be on its equator. And sometimes I saw one picture where they think there's 3 poles on one, where 2 of them are pretty close together. So it's basically, how did it crush that magnetic field? Magnetar. Black holes. So a black hole is just a little bit smaller than a neutron star, but you can't escape. Now, if you were to fall into a neutron star, on your way in, first, it would tear the iron from your blood before you even hit it. Because the magnetic fields are so strong, it would yank out the iron. So you would be staying there without any blood. That's how strong the magnetic fields are. It's not like, oh, it'll ruin your phone. No, it's gonna ruin everything. By the time you hit the neutron star, not a black hole, the neutron star, you're going at least half the speed of light. And you're gonna splat in there and not just make a dirty mess. You're gonna make a nuclear explosion that will be visible from Earth as a brightening, like a gamma ray burst. You will be something spectacular for those few seconds. I'd like to go out with a bag like that. The black hole, on the other hand,
But nobody would see it.
a black hole, on the other hand, you would fall in, and it would be silent if you fell straight in. If you fell in an arc, well, the little arc that the little accretion disk you made would glow a little bit, but it wouldn't be nearly as spectacular. If you could fall in straight into a black hole, as you got closer, there's no magnetic fields, there's no electricity, it's just gravity. If you fell in feet first, it will pull your feet off your body, then it'll pull your legs off, then it'll pull your torso, and your head will stay further away from your body, and you'll be stretched out
Like spaghetti.
like spaghetti. And by the time you hit the blackness, you would not be able to appreciate it.
I think you'd have bigger problems before then.
Here is the first picture of a black hole. Yes.
What would happen if, like, you could resist the strength of gravity on a black hole?
If you could, so if they're very big, so the one in the center of our galaxy is 4 to 4.5 million suns in mass. You could fall into that one as long as you didn't have this debris burning you up. The disk is so hot it's giving off X-rays and such. This is radio waves that it's being read, but they're giving off X-rays. If you could make it in there, the first thing you would notice is nothing different. If there's nothing around it except a black hole, and you saw the other picture as you were coming towards it. Let's go back to the other one. if you saw this is just two, I don't know why there's two, but. If you fell in, you just see the blackness getting closer and closer and closer. If you turned around, you would see the universe close in on you like a tunnel until you had a dot. And because time dilation happens at that point, you would see the universe speeding up. If you could, you would start seeing things happen at a rapid pace. To the point that you might even witness in that last dot the end of the universe, because time slows down so much that the universe goes faster. You experience 1 second per second, but the universe experiences tens of thousands of seconds per second. If you go something like 99.99s or 11.9s, the speed of light, you could get across the galaxy, our galaxy, in about a second. But it would take about 100,000 years for everyone else to want you to do that. So you can slow down time using Einstein's formula for yourself. Again, this is the first black hole ever pictured. It was used on the order of 7 to 10 radio telescopes, and they got little pictures of each little part from different telescopes and put it together using various algorithms. They had multiple people do it. They had a group here, a group there, a group here. You all had something like, I don't know, 100 gigs or more of data, and they crunched it themselves. And then they found that everyone pretty much agreed what it looked like with their own formula. Slightly different. If you put them all together, you say, oh, there's a little bit difference, but it was pretty impressive. Little stars, just gas off. This is a little star. This is what our sun will do. That's a white dwarf in the center where my mouse pointer is. It's a white dwarf. And it just gave off a little bit of puff, and then it cooled off into a white dwarf. Little stars don't do the violent death. This here is another one. And I have a second picture. It's actually way bigger than you think it is. So it gave off a little puff and then another puff. But it's not an explosion. That's just the external shells being given off. And the magnetic field made that interesting cat's eye image. The magnetic field did that. This is the southern ring, and this is the northern. No, that's James Webb's version of the southern ring. The reason I put this one in here is James Webb is the first one to notice there's 2 stars in there, not just one, which is kind of interesting. And this is the northern ring. This is our northern ring. You mentioned that, did you not, earlier today?
M57.
Yeah, there's the northern ring. It's very pretty explosion. And here is James Webb's version. You got a lot more detail in that picture. It's not letting me expand. Another version using different camera. This is what I was talking about earlier, where stuff is sloughing off of the larger star onto the smaller star. This is what makes this type 1A supernova and what makes the 83-year thing you mentioned. And when you mentioned that, I knew I had a picture for it.
The TCRB.
I want to show you something, because a lot of people say, and I say that the smaller one sucks material off. And here I have 2 sinks. Pretend like the drains are 2 stars. And I put a big star in one side. Notice it doesn't fit. I put a little star on the other side. What's actually happening is the other star is dumping on the other star. It's like having 2 sinks, and the one sink is just collecting the material. And so just so you know that's what's actually happening, is that the other star is actually dumping onto it. It's overfilling its gravity well by expanding out and getting hot, and it's dumping material onto the other star. Again, red dwarfs finally will never explode. They will never turn into a white dwarf. They'll never make that really pretty nebula. Red dwarfs will just cool and become black. And so I chose this picture because that's some blackness in there. They just cool off for trillions of years. Brown dwarfs, they can only burn lithium and helium-3, and then they shut off. They become a planet basically after that. They are just warm enough, or when I said Jupiter, maybe 80 Jupiters, it would be able to burn lithium-3, helium-3, and this is an artist concept because we can't get good pictures of these stars. The other one was an artist concept too. Nebulas only last 10 to 20,000 years. Everyone you look at are young. I mean, so 10,000 years ago, we were in the Stone Age, right? But we were not cave people. We were in the hunter-gatherer Stone Age. Egypt was forming 10,000 years ago, right? So this probably exploded back then, and they might have seen it in their sky. This is the Veil Nebula. You guys can take pictures of the Veil Nebula with your own cameras, telescopes. And the last thing is nothing. Nothing is forever. The last thing will happen is nothing, and forever there will be nothing. That is a Google years from now. Not the search site, but 10 to 100 years from now, everything will be nothing. And nothing is forever. Unless you talk to Roger Penrose, which could be another time. That is everything. That's what I have.
Thank
for
you.
guys.
Time for some questions?
Oh, yeah.
Yeah. Wow, incredible presentation, and I really was so pleasantly surprised by your level of intensity and your command of like so many things. Okay, so my question is about so extrapolations that we can make from our solar system. Okay, so our G2 or G5 star is about 5 billion years old, right? And the Earth, in accordance with the latest radio uranium radio measuring, is about 4.65. So the Earth started forming and our solar system started forming around our sun about a third of a billion years after the sun had turned on, plus or minus.
Yeah.
Okay, so looking at around in our outside our solar system now, what utility are James Webb and Hubble now used in concert together to look for other exoplanets that may be in a similar position as our G5 star? But what utility are the things that you work on as far as like looking for other we'll call it intelligent life, but is it other intelligent life
Exoplanet.
in the universe?
All right, so first, Kepler looked at about 10,000 stars, I believe it was, and found that the percentage of stars that could be visible for transients was equivalent to every star having at least one planet. What I mean by that is stars can have planets going around all different directions, right? What I mean by that too is each one only has one disk, all our planets, and Kepler found enough transients to suggest that, well, those that are going around this way to it would never see a transient, right? Those that are going up just off of oval would not see a transient either. But the amount of time it saw a transient was equivalent to the percentage as if all of them had planets and we saw those that transit. So that's Kepler. TESS is the terrestrial exoplanet explorer survey, and that one is finding things in the plane closer, and it has found, so I think Kepler found like around 6,000 candidates, and Kepler, I think, has found several thousand candidates, and you have to wait for confirmation. Confirmation is looking again another time, or using algorithms to tease out whether or not it's obvious that it could happen, that the transient could just have been a dust cloud, or it could have been a glitch in the electronics. All right, so they call it sigma. You've heard of 3 sigma versus 5 sigma. 3 sigma is suggestive of something. 2 sigma and less is nothing. I don't want to hear that. And 4 and 5 sigma means you found something. And sigma is on a Gaussian curve. the curve that gives you your, oh my gosh, I forgot the word for it. Gives you the, what's that?
Your confidence.
Your confidence level, but you know, how when you say that you're, get a grade and the C's are in the center of the Gaussian curve, you go one standard deviation. How's that one? One standard deviation away is like 1 sigma, and 2 standard deviations is approximately 2 sigma. And so we're talking way down there in the curve where it's almost impossible for each chance. That's, they prefer confidence to be seeing it again 3 times. Actually, you want to see it 3 times. You want to see it once, let's see it come again and say, okay, we see it again. And now it happened at the same period once. So you can see it 3 times. You can't look that long. I mean, think about Jupiter goes around the sun, I think it's 12.5 years. And it's 23, 28, something like that. 13, 20, 26, 27 for Saturn. So you're not going to find Saturn if you look, you know, for 5 years. You have to look for 40, 60, 80 years to get a triple hit on something like Saturn, right? All right, we don't look that long yet. We haven't been looking that long, even so, right? Right. So let's those 2 telescopes. Then what Hubble does is gets us nice images of the forming areas. Now we can see where things are forming. Can't really see planets. There are a couple of shots where someone blocked out a star and might have seen a planet. There might be a couple of those, but James Webb has a coronagraph. Coronagraph is just a fancy word. It says like you cover the star, and so it has taken a direct picture. If you do a search for a direct image of a star from James Webb, you'll see that it caught, excuse me, planet. You'll see it found a planet. Also, James Webb has the ability to get spectral data. Spectrum, as the planet is going around a star. First, what it gives you is how big is the planet, because how much does it dim the star? Another thing it gives you is as it goes across the star, that spectrum changes. You can get the spectral change of the atmosphere of the planet. Then the star itself, well, you know the star itself because there's no planet there. You get the star itself, you can subtract those 2 and see what's in the planet. Then you can actually wait till it goes to the other side, and now there's a little bit of brightening because you got the bright star and the bright planet. And then you can do it again and say, what does the element spectrum look now? And subtract the star off and get another graph. And then they can say, oh, by all these different little humps, we know it has oxygen, or it has water, or it likely has carbon dioxide. And then what's neat is the width. It's a really tight spike that says you have something there. Well, that's a kind of dead planet because it's almost impossible to have a tight spike. But by the width, we can tell how fast the winds are moving. Because if winds are moving fast, it'll broaden that line out. Because as the wind comes towards you, it makes the Doppler effect makes it be a higher wavelength, and as it goes away from you, it's a higher wavelength. So on either side of the planet, they can then see the speed of the wind. So if you hear them say thousands of miles an hour winds on this crazy hot planet, it's because of all that information I just told you. So that's how all those in concert give us all that information about the different things.
Well, if they're back here, and for life.
If there's,
If we're looking for water in a planet, I think we're gonna drill into water that may have some bacteria. If you're already finding whites outside of our solar system,
outside of the space station.
outside the space station, well, either they were carried out of the orbit during liftoff, or they're out there, and they wouldn't be similar to what I would assume that we have on our planet, because there's a little boundary there.
Yes, so it's interesting you bring that up. If we can find an evidence of life on Mars or on the space station or on another one is Europa, Ganymede, I think is another candidate, and of course Enceladus are all little candidates. You by shaking your head so you know about those. If the DNA, let's say it had DNA, and it was the opposite spiral direction. What if it had sugar, but it was the mirror image of the sugar that eaten there? That would be second gen. That'd be a different gen. But if it's the exact same direction, now you have to wonder, why is it the same?
we carry it there? Did we carry it on our space probe and we drop it on accident? Did we not clean it enough? Or did life come from somewhere else? I mean, why would it come from the Earth? Now, Mars and Venus, they actually breathe. So Meteor can hit any of those two planets, and after millions of years of orbiting, it can deposit something on each of the planets. And so there's a chance that there's cross-contamination between our planets, which would mean if we found life on Mars, which there's more recent evidence, right? The most recent evidence is the methane cycle. You hear about that? The methane cycle. So that all of a sudden there's more methane on Mars. I'm like, what? And it's in geographical locations, not just everywhere. And the newest leopard spots they found suggestive of life. And we always just say suggestive because we don't know for sure. Right? You can't know until you can put it in a microscope, put it into a petri dish, and have it grow, right? But everything you said was right. I just did more details.
Yeah, but did they analyze the bacteria?
They analyzed material. I don't remember what it was, but I know it was terrestrial. It came from the Earth. It wasn't from our space. It didn't wasn't scum cleaned up by the orbit. It was contamination from them.
It was contaminated.
But the neat thing was it lived out there. No air, no air, no protection from the magnetic field. So it's getting bombarded with cosmic rays. Yeah, but it was able to live out there.
Maybe one more question.
Yeah.
So, when you were talking about the elements that can be formed in these star formations, the highest level was iron, right?
Right.
What's the atomic number on iron?
I think it's 56, but it's
Where is
56 with its neutrons.
What is nickel?
Nickel's a couple higher. It can make nickel, but then it radioactive back down. It can make radioactive nickel, which has a few less than it wants of neutrons, and it radioactively comes back down.
So it settles down to iron.
So it's equivalent because the only difference is you have some protons that are actually neutrons. Some neutrons that are protons. It's only a couple, and it's still effectively iron.
Okay, so this would probably explain the origin of terrestrial planets.
Yep, that's correct. All the stuff above that is either from neutron stars colliding. Neutron stars are all neutrons, and as they collide, they tear apart neutrons, and they can make any side element because you started with a glob of neutrons, right? Another reason is that when they do fly apart, those neutrons coming off of that collision can also impact all the different elements that are being spewed in this calamity.
Cold.
And they call the I process and the S process. And what does R stand for? Rapid. What does S stand for? Slow. And I don't remember which one is which in the kilonova. There was a kilonova that happened before the eclipse in 17. That was detected by the LIGO. If you know what LIGO is, it's the linear. No. I think so. It's the gravitational detection, gravitational wave detector at LIGO, and they detected it because it was a very slow ramp up of gravity waves, and they said, "Oh, this is special. Everyone, point your telescopes at where this is going to happen," and then they went on. And that made something between 3 and 50 Earths worth of gold. Now, why 3 to 50? Why did they say? Well, I've heard some reports they say 3 and some say 50. But why? Well, you're trying to get a spectral reading, and then you have to estimate the volume, and you have to estimate the density, and you say, okay, maybe it's this many. So a conservative estimate is 3 Earths worth of gold, and a liberal estimate is 50 Earths worth of gold made in one collision, and that's way higher than iron. And other elements are made too, not just gold that I bring up. It's gold. Pretty things.
All right, one more thing. Kepler, did he have telescopes? And he was collecting most of his data, and he was working for Tycho Brahe, right?
I don't think he had telescopes. He had pointers. So they had basically a really big, what's it called? Astrolabe. Yeah. They just basically pointed at the tube
in the sky, so they could say, okay, it's at this exact, arc, and it's at this time of the day, and here's where that thing is, and Tycho Brahe did incredible measurements, such that, Kepler could determine that the orbits weren't circles, they were ellipses.
Yeah, right.
Yeah, and, but it took until Galileo, so we have telescopes looking at.
Tycho Brahe did the calculations.
Tycho Brahe took the data, Kepler did the calculations. So Tycho Brahe willed his data to Kepler, who was his protege. And when Tycho Brahe died, Kepler crunched the numbers and came up with ellipses.
Is there something exciting that your colleagues are working on that everyone's kind of buzzing about, like the next, big discovery from Webb or Hubble or something?
Well, when let's take limits. I don't even know. That's how I about it, because they have like 6 months to work with the data.
Right.
And then they release it. And so I don't see that. However, what is cool is we're working on the next one after Roman called Habitable Work. And so we're working on that at the Institute. The people in Instrument Lab and on one of the floors is working on what instrument would be best to put on that stuff. I think it could be that. I don't know the exact date. I thought it was closer to 2036.
Okay.
But
It's a
But
lot.
they have to plan it out way in advance. So Hubble was planned in the 70s and 80s, and it launched in 96. And then right as Hubble was originally launched in the 80s, they were working on the next gen telescope because of the next generation Star Trek. That became James Webb. And then the Roman had a name before it was called Roman.
The rules for your technology is always 10 years.
But you have to plan, right?
Yeah, I mean, you're that, maybe that's one reason they're running a free. Because that's what they had to develop it all at the top, yeah. So, I mean.
We're really glad that Kurt invited you and you did a good job.
Oh, yeah.
Thank you very much. So we're gonna take a break, and during the break, please take some refreshments. We'll figure out the extra door prizes, and I need to take a break.
That's not really.
Okay.
It's not running already. Yeah. This guy. Oh, we go, and that's why we.
I think there's some kids still here. Planetarium.
Oh.
I think all that,
So we were giving these away.
Thank you.
Thank you. That was the only stack of giving away in the fair.
They very, very difficult. I wouldn't say easy to understand, but you mean very difficult. Theories and observations and
Mainly, that's what
they hold down and made it at least comprehensive. Yeah, it was really good. And you're a good speaker. The way you move off of the podium, you're not tied to your notes, you're not tied to anything, you're moving around. I also talk about other things.
Yeah.
What do you like about Apollo 13?
Yeah, it's just.
Crazy, they were in a garbage can.
I know, that's why I put it in something where I came out.
Says, with all due respect, sir, I think they will be our finest hour. And it turned out to be, people that meet, what's up, come up today, it was good. So, that's one of my two best feel good movies. Apollo 13. What's the other one that all the time? For the same director. I have that. Oh, thank you. I pick up red for.
Thinking was that if we take Camiro's life and maybe just Draw a ticket and then the first ticket comes up first. You like that? Well, yeah. We've lost it.
Thanks.
So, yeah, so it's pick one of those and take it out as you forward.
Oh, yeah, we're not. I'll take a sticker. James Webb. Well, James Head. Now I know.
And I took one of those to use for. Oh, always,
Sure. By the way, you're on
you
YouTube.
never get these.
Yeah, I handed out a lot of these.
On YouTube.
Yeah.
I don't
Like every kid.
One of these. You don't know what
Yeah.
the basics like.
Well,
False.
yeah, until they ran out.
Of course,
Oh.
until we run out.
Thank you so much for
Yeah,
the.
so.
Yeah.
I took one of
My
these.
God,
that we
thank you
can
so
have
much.
for a library of stuff that we use for.
A little bit longer than usual, but I think we got.
Like I said, I could have made it shorter. I would have started at a different
I
spot.
had asked them.
Yeah.
Some of these.
I designed this one because someone wanted an hour and a half to talk.
Stickers and bookmarks. Well, I would love to add into a collection for outreach.
Because he said this is for the.
The big ones should
Well-
probably be for the club, but if you want to hand out the little ones, because you can't really. But it's all of you. It's just a suggestion.
Is everyone going outside right now?
No, we're just having a break. Hey, where'd everybody go?
Yeah.
I don't know, everyone just like
to be like expanding to the start.
Well, it's
Wait, is there
gonna-
Aw. I gotta work tomorrow, but that's fine. I can probably stay until like 10:30.
But, yeah, if you guys are good with it, we're gonna be cataloging our outreach materials
Okay.
for. Here, I've got one of these, we could door prize that.
All right. Here, please.
What's up, everyone?
Thank you.
Thanks. Yeah, thanks for.
I'll have Doc, like.
They
Sure.
make me shorter. I didn't know what time it was. Like I said. Okay, I gotta get that spot and then. But if you look, we're opening back up and go. I will have to continue other times. Yeah. Yep. So this is all happening.
So what this looks like.
Thank you again.
Here's something nice.
Same idea.
Okay, we should probably, wave people back in. Because I know that a lot of folks are setting up for, Star Party. Me too, I hope. Let's see if we can.
Yeah.
Yeah.
Did any warm around? It's about the same temperature. All right. Did you bring any stuff?
Oh, yeah, we're gonna get started and just be minutes as soon as I can remember which year. I brought my. I needed to do to make it go. I
think it's just. Got that here.
All of this.
Oh, you were, okay. I remember Ryan calling me and he had, I want to have a year to go now, right? I'll be in the program.
Here we go, okay, so we can wrap this up.
Yeah, Andy, let's do that.
Yeah, let's do that.
Observing to do.
Yes, we have observing to do. Okay,
For the next.
so I will just jump in.
I'm up at 7. Oh.
Okay. So, we have the freebies here. We're gonna, we're gonna be getting, started here in just a second. Somebody wants to mute their, YouTube feed, that would be great, and, if you are, somebody's got a YouTube feed on. Chris, you think you have your microphone on?
Might be the Zoom.
Yes, it is the Zoom. And it's not mine. So if y'all that have this thing going, if you could, is yours tuned into the YouTube? Okay, I don't think so.
It's coming from that.
Well, right, it is, but I don't know.
Is it back in here maybe? No?
That is muted. All right, all the more reason to get it over with here.
So strange.
Actually, we could cut off the YouTube.
Yes.
Yeah.
Oh, yeah. But if they don't- Bye, everybody. Bye.
That's the YouTube we're cutting. All right,
Bye, YouTube.
I have not cut off the Zoom. All right, so, at